Imagine an atom. Most of us picture a tiny solar system, a solid center with little electrons circling it in perfect, predictable rings. This early planetary model was developed by a physicist named Niels Bohr. It was an essential starting point for modern science, helping early researchers visualize how atoms work. However, we now know that electrons do not actually travel in flat, perfect circles. If you tried to track an individual electron, you wouldn't find it moving like a train on a circular track. These particles operate on unpredictable probability. To understand how matter is truly built, we have to look past the solar system and see the atom as a collection of shimmering clouds. Think of a plucked guitar string. When it sits still, it is a single sharp line. But when it vibrates fast enough, you don't see a line anymore. You see a blur. You can't pinpoint exactly where the physical string is at any specific microsecond. You only know that it exists somewhere within that blurry shape. Electrons behave similarly, vibrating as three-dimensional blurs around the atom's center. In chemistry, these shapes are called orbitals. Chemists define an orbital by drawing a boundary enclosing where you are 90% likely to find the electron, a map of its favorite hangout spot. Atoms are made of these overlapping layers of vibrating energy, stacked together to form the solid structure of everything we touch. The lowest, calmest energy state an electron can occupy is called an s orbital. It is a simple, hollow sphere located right at the core of the atom. Because electrons have a negative charge, they push away from each other. That initial spherical room only holds 2 electrons before crowding forces them apart. Once full, new electrons move further out into higher energy p orbitals, shaped like pinched balloons. To minimize crowding, these dumbbells align along 3 different axes, up and down, left and right, and forward and backward. These strange shapes emerge as a natural response to crowding. They're the physical result of electrons finding the most comfortable balance between staying close to the center and avoiding each other. As an atom collects more electrons, it fills these shapes in a strict sequence. It is like building a musical chord by playing the lowest, deepest notes first, and then stacking higher keys on top. The sequence always starts at the bottom. The atom drops its first 2 electrons into that foundational inner sphere, the 1s orbital. When that is completely full, the next 2 electrons move outward. They occupy a slightly larger spherical layer wrapped around the first one, called the 2s orbital. Any additional electrons beyond those first 4 are pushed out into the dumbbell shapes, the 2p orbitals, stacking energy layers outward into space. When scientists map out exactly which layers are filled in which order, they call it an electron configuration. It is the exact sequence used to construct the atom. Keeping track of all these stacked spheres and overlapping dumbbells sounds complicated. How do chemists remember the sequence without getting lost? Scientists use the periodic table as a map showing how energy layers stack up. The far left columns form the s block, 2 columns wide for the 2 electrons it holds. The wider right section is the p block, 6 columns wide for its 6 electrons. The periodic table serves as a physical cheat sheet. It allows you to read the invisible architecture of matter simply by pointing to a specific box on the grid. To find nitrogen, row 1's 2 spaces put 2 electrons in the inner sphere. In row 2's left block, 2 spaces fill the 2s sphere with 2 electrons. In row 2's right block, counting 3 spaces to nitrogen places 3 electrons into the dumbbell shapes. If we write out that path, we get a simple code: 1s2, 2s2, 2p3. That sequence is a direct translation of nitrogen's physical location on the grid. By letting go of the solar system model and embracing the rhythm of vibrating probabilities, the complex structure of the universe becomes predictable and elegant.